Cool, thank you, Nick. Thanks everyone for staying around in this last session. All right, let's get it started. Hey, I'm Jay from the University of Washington. I'm an Asian male with black hair, wearing beige sweater, blue pants. And today I'll be presenting our work on CookAR, an AI-powered AR prototype that can overlay affordance augmentations on kitchen tools to support low-vision cooking. So, cooking is an essential activity of daily life, independence, and health. But for people with low vision, using tools like sharp knives or hot pans can often be a challenge. So let's imagine you're in your beautiful kitchen. You may commonly boil or fry your ingredients. However, low vision individuals identified hot tools as a key source of hazard. How do they know which part of the tool is dangerous or safe to interact with? And let's take a look at another example. You may often cut ingredients. Same thing, again, low vision people may have trouble determining which knife part is hazardous or safe to hold. To address this, we designed and implemented CookAR, a novel wearable AR prototype with near real-time affordance augmentations to support safe and efficient interactions with kitchen tools. The CookAR system is mainly comprised of three parts. First, an egocentric affordance dataset, which we manually collected and annotated. Two, an accompanying fine-tuned affordance segmentation model. And three, a fully functional AI-powered wearable AR prototype. First, to assemble our dataset, we started with Damon et al.'s Epic Kitchens dataset, and this dataset contains 100 hours of egocentric videos of sighted people cooking in their homes. As the Epic Kitchens dataset is quite large, we first used YOLO V8 to find key frames containing cooking-related objects, so spoons, knives, forks, and etc. We then removed frames that are similar, excessively blurry, or just irrelevant. Irrelevant meaning YOLO V8 detected an object, but there really isn't a cooking-related object. To label then the selected frames, we used RoboFlow, an online computer vision tool that supports labeling automation using the Segment Anything model, or SAM. This allowed us to easily select and segment an interactive part of cooking tools, and then add corresponding class labels. So in this case, a knife blade. We labeled 18 distinct classes of kitchen tool parts that are commonly used by blind and low vision individuals according to prior literature. These are knife blade and handle, spoon bowl and handle, fork tines and handle, scissor blade and handle, ladle bowl and handle, spatula head and handle, pan base and pan handle, cup base and handle, and carafe base and handle. I had to learn all that. After augmentations and after image augmentations, our dataset had a total of 10,152 images. Then with this kitchen tool affordance dataset, we fine-tuned the RTM-DET model, and specifically its large variant. We chose RTM-DET, and it's a state-of-the-art instant segmentation model, as affordance segmentation models are less common and often intended actually for robots. By fine-tuning an instant segmentation model on a dataset with affordance annotations, our RTM-DET INS-L Cook model can mimic an affordance segmentation model's capabilities. And here's just a demonstration of our fine-tuned model running on a video wall by Damon et al. As you can see, it is not just looking at traditionally whole object segmentations, but also looking at its individual parts. To generate visual augmentations then that align with object parts in a 3D space, we had to build a custom system that combines both the Z Mini stereo camera and an Oculus Quest 2 VR headset. The reason why we use Z Mini for pass-through and everything else is because it gives us access to raw frames as well as depth through binocular depth estimation. We stream raw frames from Z, specifically its left camera, to an external server with GPU, which performs our affordance segmentation model. The resulting data is then sent back to Quest 2 headset just for rendering, and this whole process takes about 20 to 25 frames per second, so near real time. The CookAR AR prototype then overlays affordance augmentations in near real time. Green indicates a grabbable area, and red represents a hazardous area. And here is our low vision participant using CookAR during a user study session. With CookAR, we conducted a 3-part lab study with 10 low vision participants. In part 1, participants were asked to compare 3 conditions in a tool grabbing task. We asked participants to pick up 5 randomly chosen cooking tools with 1, real-world baseline, meaning without CookAR and with their daily methods and their typical methods in daily life, such as wearing corrective lenses. 2, augmentation baseline, which is similar to CookAR, but instead using whole object augmentations. Playing again. On the right side of me, whole object augmentations, and CookAR, which of course displays affordance augmentations in both red and green. In part 2, participants completed a freeform cooking task where they cooked macaroni and cheese using CookAR with affordance augmentations. Participants followed a 9-step recipe. We supplied them with dull knives, and we avoided the use of fire for safety purposes, and as well as we couldn't get IRB approval. In part 3, we asked participants to co-brainstorm the future of CookAR. We presented design probes of various augmentation designs, such as some mix and match of outline, solid augmentations, and arrows, and then we asked participants for some feedback. A key finding is that visual augmentations should maximize utility and minimize visual clutter and confusion. Let's expand this on this a little bit in the next few slides. First, well, this means affordance augmentations are not always necessary. For complex tasks requiring object interactions, affordance augmentations are great. For example, in cooking. Participants also mentioned use cases such as gardening, playing board games, and interacting with appliances. However, for simpler general visual perception tasks, whole object augmentations could be better. These include avoiding obstacles and locating an object. Participants also provided some design recommendations. For this initial CookAR prototype, we just used filled mask overlays to mimic computer vision outputs. However, participants desired the following. Participants preferred some combination of solid and outline augmentations. Participants liked solid color overlays for grabbable areas, as this enables fast perception and action. However, participants wanted outlines for just about other affordances to minimize distraction and confusion and occlusion. For example, participants wanted to be able to see the inside of a ladle or a pot to see what is inside. However, solid augmentations would often cover the view inside. In terms of colors, augmentations should be colors with high color contrast against the environment. So for example, a common problem participants mentioned is a yellow butter on a brown wooden cutting board. Beyond visual assistance, participants also suggested short yet noticeable audio cues such as beep beep, as visual warnings could be easily missed by someone who is low vision. Lastly, future systems should support extensive personalization capabilities such as voice-based control and automatic adaptations. So just to give you guys a couple examples, users should be able to toggle automations on and off, switch between colored and solid colored overlays and outline overlays, change the outline thickness, and even color. Additionally, several participants wanted the system to automatically adapt to user actions and surroundings. So for example, changing colors of objects automatically to enhance color contrast, highlighting parts that will be cut as the knife gets close to the item or ingredient that it's supposed to cut, or turning off grabbable augmentations once the users are already holding the object. Beyond grabbable and hazardous areas, participants also identified 5 additional tool affordances. Entry. Entry area affords a part to aim at or pour in. This could be the rim of a cup or a pot, and the opening of a carafe. It should be overlaid with outline augmentation so that users can see the inside of the relevant object. The exit area affords taking or pouring something out. It often requires accurate alignment with entry area of another object. This could be the spout of a carafe or the rim of a ladle. Entry and exit areas can be the same. For example, think about the rim of a cup. Containment area affords holding some content in. Participants wanted augmentations to represent some content amount. So for example, how much content is already in a ladle can be represented by a bar, almost like a partially filled bar or a bar graph even. An intersection area affords where two objects touch or intersect. So I think I already gave you an example already. An entry area of an object and an exit area of another can intersect. Another example could be a knife can intersect with an ingredient. An intersection area can also benefit from some kind of a measuring line, especially if a recipe requires a specific amount. So for example, butter, so how much tablespoon. Lastly, activation area affords ways to control different features of objects. So for example, buttons on a carafe or a coffee machine. So that sort of concludes my talk about CookAR, but before closing, I do want to have a couple of discussion points regarding the challenges that I kind of faced in implementing an AI-powered AR solution such as CookAR. So our fine-tuned model does outperform the baseline model, the standard RTM DET model, in segmenting cooking tool affordances. However, it still had segmentation and tracking inaccuracies, and that's why you see certain augmentations flashing on and off. Additionally, due to system latency, as you can see, CookAR could not keep up completely with participants' head motion. So what does this really mean for HCI and CV and for us to kind of be together? Well, this is acceptable for an initial prototype. Perhaps these technical limitations will just be a matter of time. However, we should begin to think about AI's potential real-world use cases, human needs, and integration to different hardware platforms such as Wearable AR to enable use in practice. So for example, in this case, how can AI models augment a person's first-person point of view to support them in any way? Thanks for listening.
Thank you, Jay. So audience can ask questions.
Fantastic work. Yeah. So the first question is that the user study, you have a baseline that the user do not use augmentation, like any augmentation, and then you have the whole augmentation, and then you have the affordance augmentation. So what exactly is the quantitative performance there? Like does the user with this, like what's the quantitative measure, right? They cook faster, they cook better. What's the quantitative measure here? And the second question is, like, it seems that you really build a symbolic model of affordances. So that's really cool. Have you think about like just try it on robotics? Like you get a machine to cook. Like if your affordance is really well, then the machine should be able to cook, right? Like to the extent that you are able to make a machine cook. Would that be another benchmark that you can look at? Yeah, thank you.
No, thank you for the great question. So to answer question one about sort of like study findings and study results, so because CookAR is an initial prototype and it has certain limitations like latency and computer vision issues, a lot of people actually, so to say, quantitatively speaking, they said, hey, I kind of dislike this because it takes a little bit of time to catch up. It's sometimes inaccurate, right? So that's why I think a lot of the times we actually defer back to in the paper for qualitative findings. And a lot of our qualitative findings are sort of about the design recommendations that I mentioned, as well as sort of how people's general perception was for a technology like this, assuming it does get better. To answer the second question, I think that'd be a great benchmark, to be fair, because we did perform a technical evaluation saying that, hey, like fine-tuning this on our data set actually did improve its performance for detecting affordances. Maybe robot could do better, right? Robots are a little bit slower than how people's head move, so maybe that is an interesting metric that we just did not take into consideration. But thank you, that's great.
Do we have time? Yeah. Hello, thank you for the great presentation. My name is Yotam from the University of Tokyo. I am a low vision user, and my question is this something that people can actually use? I can tell from my own experience that to cook for low vision users, you rely on familiarity. So you know what you have, you know what equipment you have. For example, I place my knives, I have two knives. I place my knives exactly in the same places all the time because then I can easily reach out and grab the knife I know I want to get. So my question is, like, do you think that this is something that low vision users will or should utilize when they are in their own home?
That's also a really good question. So I do have something that the participant said, but before that, obviously not in this state, right? But hopefully with improvements, perhaps. Because, so for example, one of the things that one of the participants said was they like to color code their tools, for example, so that they can easily find them. But this is essentially doing your sort of color coding for you. And when that could, prove useful is just, for example, if you're in a foreign kitchen and not in your kitchen, and you're about to cook and you need the color coding, which they do not have, this could, for example, apply color coding for you instead, if you can, of course, personalize the colors as well. So I think there is definitely a use case for this. Of course, not in this state, but once enough improvements are made in both hardware and it's not connected to a computer, and of course it gets a little bit faster, then I do see certain use cases like that, for example.
Thank you so much.
Thank you so much.